Principles of Bioproduct Separation, Module 11, Ultrafiltration and Electrophoresis, Segment 3, Electrophoresis. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about the basic ideas and ultrafiltration. In this segment, we will discuss about electrophoresis. The most common electrically driven purification is electrophoresis, caused by solid motion under the influence of an electrical field. The simplest form of apparatus for electrophoresis, as shown in the figure, consists of two electrodes to apply the field across a thin chamber. The classical decellulose cell used for protein separation in aqueous solution, shown in the figure B, whereas a modern gel electrophoresis apparatus is shown in the figure C. One major problem in electrophoresis is to avoid mixing. Mixing caused by a gas released at the electrodes can be avoided by placing the electrodes in separate compartments, as in figure B and figure C. Mixing caused by separating different fractions of solution after the electric field is applied can be minimized by careful design. A different cause of mixing, and the most important, is the free convection caused by electrical heating. Using very small currents gives small heating but very low separations. The effect of heating can be correlated in terms of the Rayleigh number, as shown in equation 23. If the Rayleigh number is small, then the flow will be small or non-existent. If the Rayleigh number is large, then the flow may be significant. There are two ways to make the Rayleigh number small. One has value in the laboratory and the other has value at a larger scale. A well-known laboratory method is to perform the electrophoresis in a gel which makes the viscosity very high and hence removes the free convection caused by the electrical heating. A variety of gels can be used, but polyacrylamide is often used. After the electrophoresis, different solutes can be separated by cutting the gel into parts. The solutes can be eluted from the gel and purified further if necessary. The difficulty with the gel electrophoresis is that it is tedious and expensive to operate at a large scale. Setting up the experiment usually requires a large amount of hand labor. The way to make the Rayleigh number small on a larger scale is to use membranes. For membranes, the characteristic length L is the radius of the membrane pores, which appears with the fourth power. Thus, small pores produce small Rayleigh numbers. In many cases, the separation achieved by electrophoresis through a membrane is too small to be of interest. A convective flow countercurrent to the electrophoretic motion may improve the separation. For the next segment, we will discuss about electrodialysis and isoelectric focusing. Until then, I am Yusuf from Institut Teknologi Bandung.